thank you for coming this afternoon, this morning. It's my great pleasure to introduce Dr. Zhigang Peng, coming to us from Georgia Tech. Dr. Peng got his bachelor's in geophysics and a bachelor's of engineering from computer applications from the University of Science and Technology in China. He then went on to get a master's degree in electrical engineering and a Ph.D. in geological sciences in 2004 from the University of Southern California, working with Yehuda Ben-Zion, who went on to do a postdoc at UCLA, and then went to be faculty at Georgia Tech, where he is now. Zhigang has had a tremendously prolific and successful career so far. He was awarded the Charles Richter Early Career Award from the Seismological Society of America. He also received an NSF CAREER Award and the Young Faculty Award from Georgia Tech. Zhigang, for some time now, has been the official editor for the Seismological Research Letters, where he has done a great deal of work. From my perspective, one of the really exciting things is he has instituted a new column of articles for seismic deployments that allows you to document your deployments as soon as the stations are in the ground instead of waiting for those first papers to come out, and that's valuable for a whole host of reasons. It gives us some good documentation on many data sets that previously were hard to get together. He's also been associate editor for the Bulletin of the Seismological Society of America and for JGR. Zhigang does a lot of research on the role of fluids in earthquakes and interactions of earthquakes with other dynamical earth forces, and so today he's going to talk to us about that. Okay. Get that? All right.
Let me make sure the mic down. Hello? Can you hear me? Hello? Okay, we're good. Okay. And make sure it's working. Okay, well, thank you, Laura, and thank you again for inviting me to come here. I was here actually a few years ago to give a talk. So today, basically, I will hopefully, in the next 45 minutes, I will talk a little bit about what our group have been working in the past few years. And in particular, so I'm a seismologist, and if you want to classify me as I'm more like a source seismologist. I'm basically using seismology as a tool to understand the earthquake source, which is those type of seismic event that generating seismic waves. So I'll try to maybe stay on track and maybe tell you 2 or 3, depending on how fast I go, stories about what we have been doing to using massive amount of seismic data and try to do some sort of what we call data mining, to basically identify small, tiny earthquakes that are otherwise, either not made it up to the catalog or not being detected, and how we can use that to understand processes inside the Earth. So I kind of highlight 2 words here. It turns out maybe some of them are fluid-driven, some of them are not. I will tell you a story about that, and also change the title slightly. Previously, I write the title in the Crust, but it turns out that I started also working on some seismicity that is very deep in the mantle, so it's generalized to be inside the Earth instead of only in the crust volume. So hopefully this works. One of great things about working in seismology right now is we have a huge increase of amount of data being collected nowadays. Those are mostly through efforts such as stations that are permanently deployed. Like in the case in Japan, you have about 8 to 1,000 stations. Every 10 kilometers, you have a very high quality like ball stations. Those are the so-called HiNet and also some storm motion sensors. You also have projects like the US Array or also similar effort of China Array, where they're putting temporary station, every a few tens of kilometers, high quality broadband sensors, put in there for a few years and move on, kind of piggyback in a fashion across the entire continent. So those type of data are providing us very valuable information about, not only the earth structures, but also telling us about, where earthquakes happen or where some interesting seismic event that previously haven't been detected. So again, one thing I was going to tell you, hopefully, is some of our recent effort of, how to harness useful information out of those vast majority of the seismic data. So I'm going to again do a quick kind of seismology 101 to tell you how we detect seismic event. It turns out that that's actually one of the most important and question the problem we have to face is that once you record seismic data, the first thing you need to do is to find out the good stuff, okay? Which we normally term as signal, but of course everybody's signal definition is different. So for us, it used to be like the signal is a event which something look like this. You see in the seismograms. Now you have several approaches to this. One is that you hire an undergrad or graduate to pick the phase. Any site into that type of effort. It takes a lot of time and effort, but after some time you get used to that. Okay, you pick phase by hand, or you use some sort of automatic ways of doing this. Here's just one example. You develop some sort of characteristic function. In this case, it's a so-called short STA, which stands for short-term average over long-term average. Basically, you're looking for a transient change in the waveforms that tell you that maybe there's something going on. So in this case, you have once you set up a threshold above which you said, okay, I have a phase. You don't know what it is, but you have an event or you have a phase coming. And in most cases, the signals are recorded by more than one stations. So in this case, and also one station normally has 3 components. You have multiple components as well. So after some time, you start to have an event that are recorded by multiple stations. And then you start to do some sort of what we call association. You somehow put them together and say, okay, this is one event, and then this is the P wave and the S wave, and then and then start to do event localization. You locate where they come from, and then derive something other product. Like the detailed source properties, the moment tensors, etc. Okay, so this type of approach generally works in a case where a region is relatively quiet. Let's say you have a few events per day. This is no problem. You can at least capture most of the event. However, if you look at a problem like this, where you have a case, this is called the earthquake swarm happening somewhere in New Zealand, I believe. Earthquake swarm is basically a case where all of a sudden, in a region, it's being lighted up by seismicity in a very short period of time and space. And most times, the earthquake swarm turn out to be driven some kind of external process like fluid, or if you have a slow creep event or something. Those are probably the driving force for the swarm. But nevertheless, when you have a case like this, an event is almost on top of each other, and hence that it will be very difficult for you to apply the previous technique, because the previous technique require you to have a relatively low background levels. So if you apply this previous STA-LTA approach, you're probably going to record those large ones, because they clearly stand out of the crowd. But many of the small ones that are buried or on top of each other, you cannot detect or locate them. Okay, so it turns out that many of them are undetected if you use the previous approach. Another example is something like this, which I will, in the second part of the talk, I will elaborate a little more. This is a signal recorded, it's about 1 hour recording, recorded by Boho seismometer in Japan. And the signal, I'll give a name called deep tectonic tremor. It used to be called non-volcanic tremor, to be distinguished with volcanic tremor. But nevertheless, those are signals that are nearly continuous, vibrations, and also doesn't have, let's say, clear phase arrival. But if you look carefully, there are sometimes you have phases. But the events are right on top of each other, such that it's very difficult for you to separate out, this belongs to this event and this one belongs to that. So what people normally do is take a chunk and try to call the entire thing as a event and try to locate it. But nevertheless, if you use the previous STA-LTA, that didn't work in this case as well. So you have to basically use some alternative or other ways to detect those events. So one of the things that, again, we have been working in the past few years, we probably not only including people in our group, but also including other people as well, is to use this approach, which we call as template matching measure. Okay, the idea is pretty simple. Basically, let's say if you have a event or seismic event that are determined by somebody else, by a graduate student or by STA-LTA, you have some event to start with. So this is the waveform. Of course, let's say maybe this is the P wave, this is the S wave. If you cut a chunk of data that corresponding to the signal for this event that you already identified, so you have locations, you know where it happens. Now you take this event and doing some sort of running cross correlation across the longer, like say, continuous waveforms. And so you're going to end up getting is some sort of running cross correlation functions. So the idea is that in many cases, not all of the cases, earthquakes tend to occur in places they used to occur. Okay, so many places that they just keep repeating in the same region or similar region. They don't have to be right on top of each other, but the waveform for many of the event would be somewhat similar to the event that you already identified. So the idea is that you use those events you already have, and then you scan through the data using this technique to find the event that has not been detected. Okay, but of course, if you look at the cross-correlation trace, you can see it's kind of noisy because it's very easy to get a high correlation with data like this, and with you can correlate that with noise. You can get a relatively high cross-correlation as well. So this method will not work for single station, single channel. However, in many cases, earthquakes are recorded by multiple stations, multiple channels. So if you do some kind of proper time shift, you shift every cross-correlation function to the origin time when the event happens, and then you do some kind of simple linear stacking. What you end up getting is that at times where there are events, then of course everything will line up. You're going to get resulting in relatively high cross-correlation values. In times where there's no event, or the event is too far, then you will not correlate with the master or template event. And hence, by using this kind of very simple technique, you can take in the event you already know and scan through the continuous data and try to detect those events that are otherwise not being detected by the technique. So, of course, once you have this function, you can set up a threshold about which you believe that, it's unlikely to be a random detection or forced detection. Here are just some examples of showing how the technique works. Again, it's a so-called network average. So you're not looking for a single station, single channel. You're looking at many stations. The more, the better, right? So the red, green, and blue are some of the so-called template. Your target. You already know where the event is. We're scanning through the continuous data. This is in this case is it's a magnitude 6 earthquake on the San Andreas Fault in Central California. So in that case, this is during the first 200 seconds. You can see that waveform matched with the data very well. Has a mean cross correlation of about 2.8. It's a scaled cross correlation. The 1 means perfect self detection. So that means that these events probably are very close, if not right on top of each other. So by doing this, we can not only detect the event, but in addition to that, we can also locate them. The simplest way to locate is you simply assign the location of the template to the detect event. In addition to that, you can also determine the magnitude by looking at the amplitude ratio. So by the end of the day, if you have a lot of template, let's say in this case we're using about 3,000 or 4,000 template, we scan through like say days or years of data, and you can probably normally find 5 to 10 times, sometimes a few tens of times more events that are normally reported or in the standard earthquake catalog. Of course, this technique works best in times where you have a lot of activity. So in this case, it works best in earthquake swarm period, or works best in times, let's say, right after a big event. Okay, because that's the time where your catalog is the most incomplete. But it turns out those are the times that are most important, because if you want to understand how earthquakes trigger each other, and also understand for example how fluid might driven swarm activities, you want to detect and find those tiny small events as possible, because it gives you a much better spatial temporal coverage. So that's kind of the quick summary of the technique. So in the next, again, maybe 30 minutes, I will probably give 2 or 3 examples about how we can apply this technique at different tectonic settings, and use that to understand what we know and what we don't know about Earth processes. So the first topic, first story I will tell is to look at intermittent depths earthquakes. So this is a map of global seismicity, I guess, in the last 10 years, and it's color-coded by depths. As most of you know, that earthquakes normally occur in a brittle portion of the crust. So mostly are a few tens of kilometers depths. But of course, occasionally we also get some deep earthquakes. In that case, deep, if you loosely define, is deep being deep, larger than the cyclic crust, 70 to 100, 300 kilometers. We call them as intermediate depths, and below 300 kilometers, we call them as deep focus earthquake. Of course, different people's definition might be slightly different, but that gives you a rough idea which type of event we're looking at. So if you look at, again, the yellowish are probably intermediate depths, and then the green and the blue are the deep focus event. If you look at them, they mostly occur in subducting zone, which is not surprising because that's where the coast slab is subducted into the mantle, and so the deepest seismicity we know is about 700 kilometers. Okay, so we know roughly spatially where they occur, but of course, turns out that there are still a lot of unknown factors about those events. It's apparently in the relatively high temperature and pressure region. Why do we did brittle type event? And if you look at the waveforms, they behave somewhat similar like shallow earthquake. They are predominantly a shear slip event. Okay, so how can you get shear slip event at such larger depths? Of course, there are many models that have been proposed. And, I won't go into the details of that. But generally speaking, you need to have some kind of weakening mechanisms for the earthquake to occur at such depths. So so today I'm going to look at this region. This is in Hindu Kush and Pamir region. This is a region where you get seismicity, intermediate depth seismicity up to about 250 to 300 kilometers. So there's no seismicity deeper than that, but you get a lot of events over there, and they occur repeatedly. And we don't know what's going on, so we want to understand, why they're there and what do we know, what we don't know about the process. This is again a cross section of a subducting zone. So again, hopefully give you some idea where do we see seismicity. Of course, you get the shallow portion. This is the megastrata, in the crust. Crust, and you started sometimes see this so-called double seismicity zone. Sometimes it shows up, sometimes it doesn't, and goes up to about a few hundred kilometers. And then you also get perhaps another group of event that shows up at a depth of about 500 to 600 kilometers. And so if you look at again the seismicity distribution, this is the number of events per year. You can see that it decays exponential ways depths. So you don't have much event at a depth range of about 300 to 500 kilometers. But then you get another group event at a depth range about 600, and the deepest is about 700 kilometers. So, this type of seismicity again, has been observed, but the question is, why they're there? So, like I said, there are predominantly shear slip events. Another interesting observation that generally people believe that's true is that many of the deep focus and intermediate depth earthquakes does not have many aftershocks. So again, here aftershock means, after a big event, you have a lot of smaller size event in the region where the main event happens. And so it turns out aftershocks are almost a ubiquitous observation for shallow crust event. If you have a magnitude 7 or 8 event, you get a lot of events in the surrounding rupture region. Now, for deep event, turns out that especially for very deep event, sometimes you have a magnitude 7 or 8 event, and there's no single aftershocks being recorded. The question actually we're trying to address here is that, is it because, first of all, there's no aftershocks, or maybe there are events, but somehow get hidden either by the coda or by something else, so that maybe they are there, but perhaps because of the distance that you are not being recorded. It's recorded, but you are not being detected. So that's a reasonable question to ask. So we use one example to demonstrate. So this is a starting region. Again, this is Hindu Kush and Pamir region. The color code here tell you the seismicity depth. So you can see, from the cross section along, longitude and latitude, you can see there is a relatively steep dipping plains outlined, so that it goes rapidly from near a few tens of kilometers to about 200 up to 300 kilometers. So if you look at the cross section from P-wave tomography, you also see interesting features. So if you focus on the AA prime region, this is of course a previous study, you see relatively high P-wave velocity, which normally we associate that with a subducted slab. And these depths go up to about 500 to 600 kilometers. But of course the seismicity actually shut it off at about 300 kilometers. So this seismicity is clearly associated with this sort of downgoing slab. So if you look at different cross section, you get different gently dipping slopes. So the current idea is that you may have kind of this kind of double collision or subducting process going on. You get this process. This is associated with the Indian craton is diverging very rapidly at almost like vertical drips at this region. At the other region, the slope is dipping slightly gentle, but it's about also going towards this direction. So the question is, again, in particular, this region is where we focus. This region, over the past about 100 years, generally every 10 to 15 years, you get a magnitude middle range 7 earthquakes. And the most recent one occurred in 2015, I guess October. It's a magnitude 7.5 occur right over here. But of course, if you look at the USGS catalog, you can easily find out, the previous one is about 2002, and then the earlier one is about 1993. So every 10, 15 years, you get this kind of middle range magnitude 7 event. If you look at the waveforms of those events at very far distance, so this is a work recently published by a group at Caltech. What they found out is that those events are very close to each other, if not right on top, and because the waveforms are so similar. And so you get a region that is probably no more than 50 kilometers range that you get those very large magnitude 7 events occur. And of course, there are also sometimes smaller events, in the range of magnitude 5 or 6 events as well. So why do we have event here? That's an interesting question. Now, one of the things that we are looking at this is when we look at this event, which is magnitude 7.5, when we look at the catalog, which in this case, there's no regional catalog. So I'm looking at the global catalog from USGS. In the first hour or so, there's only one event listed here. It's about 4.8. And it's about, if you look at about the months, there's about 20 to 30 events. And so because here, the magnitude completely is, you start detect event at around magnitude 4. So you get, about 20, 30 events. There's not much you can do with that amount of data. However, if you look at the waveforms, so this is a broadband station, I guess, in nearby country, Tajikistan. It's about 200 or 300 kilometers away from the epicenter. Of course, the main event kind of saturated a bit, but if you look at, this is raw data. It's broadband recording. You can't tell too much. However, if you apply a simple high-pass filter, if you remove those longer period waves and then take an envelope function, you can start to see these spikes. It turns out each of the spikes are corresponding to a earthquake occur very close to the epicenter. And so those are likely aftershocks. And many of them are, of course, probably hundreds of them occur during this time period, and none of them are detected. Of course, if you look at the spectrogram, you also see these kind of spikes. And so the event is there, and it's not being listed in the catalog. So this is actually hopefully it works, animations with sound, and sometimes I do that as well because we normally take the data and we play it faster so that you can map those lower frequency range into higher frequency range so your ear can hear. So again, our ear can pick up signal from, let's say, a few tenths of hertz up to kilohertz range. So normally you can't hear the seismograms, but if you play it faster, like old days when you have a cassette player, you play faster, you hear the high pitch signals. So let's see if it works, and if hopefully it won't scare you. Sorry, too loud. So that's the main event. Of course, you feel the power. Now you start to hear this. So each of the time you start with the higher pitch and then followed by lower pitch. So the higher pitch one is the P wave, and the lower pitch is the S wave. Because of distance, you can hear it. So that's the event that are listed in the catalog because it's the largest. Okay. But I'm sure your ear can pick up more events that are detected. So the events are there, and also you can see that they actually look very similar. So what we end up doing is basically use the same approach. We have, like in this region, there are about 10, 20 events after the main event that are listed in the catalog, but we also went back in time. And so in the end, we selected a region that's about like 200 kilometers wide. So in total, we have about 300 events. So it's not great, but it gives you a relatively good coverage, spatial coverage. And we take each of the waveforms, we chop, let's say around the P and the S wave, and then we simply take this template and scan through data and look and see where it matches the best with the continuous data. And if it has the match, in this case, it give you a mean cross correlation of about 0.6 or 7. That give you a reasonable confidence saying that this is definitely, or there's event here. Now, one thing we did beyond this simple matching is that if we zoom in around the time where you have the detection, those are individual cross correlation functions. You can see they line up almost nicely at the time where you reach the detection. However, if you zoom in further, you find out that actually that they're not perfectly lined up at time 0, which is where your event is. If it's exactly at time 0, that means they occur at almost the same spot. If you look, their peak cross correlation is slightly shifted, by a few fractions of a second. Okay, those turn out to be very important because that give you the so-called differential time between your master event and the event you detected. So you can actually extract those information out and then put it into a scheme to do something we call relocation. So now you have a master event which presumably you located reasonably well, and you look at the perturbations of the detected event with respect to the master event. So you can end up getting a location that are relatively accurate from what the event you have detected. So this is a quick showing of the results. So out of the, remember, the red ones are the events are listed in the catalog. So you can see that started with, this is the magnitude plotted with time and plotted with log time since the event. So you can see that again you start to record event of magnitude 4 in the catalog. But of course, with this technique you can push the magnitude down to about 1 to 2 range. If you look at, you determine the so-called magnitude of completeness, you can say you can pretty much sure it's about completed about 2.3 to 2.5 or so. But of course, as you know, at the early time, immediately afterwards, you probably also are missing some smaller ones as well, because those smaller ones probably occurred, but it's being hidden behind the big ones. Okay, so this technique, of course, you can't detect everything, from what happens, but at least it's much better than what has been reported. So out of this, remember, originally you start with about a few tenths. Now you have a few solid. With those events, you can start to look at statistics and look at its spatial and temporal evolutions. For example, here we can easily fit a so-called Amore law decay, which is the power law that are generally characteristic of after decay. When you feed that, you get almost a perfect value of 1. So in this case, the aftershocks of this intermediate depth earthquake looks very similar to crustal type earthquake. In addition, this is just one way to check and see how well you're doing. Again, this is the events that are listed in the catalog. The dashed lines are the event we detected. Okay, so you can see, I think we did a reasonably good job of capturing those events, after a few hundred seconds. In the first few hundred seconds, you can see that there probably are still events there, but we're not detecting anything. The reason is because we are looking at a frequency range between about 1 to 10 hertz or so. You can see that during the first few hundred seconds, you still have a lot of coda from the main event. Hence that those events probably get hidden by the coda. So if you really want to detect those early events, you probably have to push to higher frequency range. And so that's something we're still currently working on. But nevertheless, starting about 500 or 600 seconds up to a few days later, you come up with a much better and complete catalog as compared with before. So finally, let's look at spatial distribution. So here it shows the map view. It's stretched a little bit in this direction. So there's an on strike versus the strike perpendicular direction. If you look at this is the cross section, this is the depth view versus the on strike. So this event, the epicenter start from somewhere here, and but the majority of this sleep, based on finite fault inversion, is to the west. So this is from the USGS finite fault inversion. So the largest sleep here is about 5 to 6 meters. So the main events start from here, but it's predominantly propagate to the west. If you look at the aftershocks, those are all aftershocks. You can see that the mortise forms a near vertical plane, and it predominantly forms to the west of the ruptures. And this is actually very similar to crustal earthquake as well, aftershocks. And it turns out that most of in many cases when you have a very good spatial resolutions, aftershocks turn to have some sort of anti-correlation with the main shock slip. The region that sleep the most don't have many aftershocks because the stress has been released. Well, the region adjacent to that have experienced the highest stress variations. That's normally where you get most of the aftershock as well. So at least this is roughly consistent with what we know about shallow earthquake as well. So at least in this case, we think that the behaviors, aftershock behaviors for this sequence seem to be not much different as compared with shallow crustal earthquake. So to kind of wrap up a little bit, so what people have done, again, this is from the Carter group's result. What they found out is, if you look at those magnitude 5 events, magnitude 7 events every 10 years, if you summarize the cumulative moment and you do some simple calculation, you find out that actually the best fitting slope give you roughly about 10 centimeters per year of strain accumulation. This is about a factor of higher than the crustal, like the convergence, which is observed on the surface, which is about 1 centimeter per year. So one of the hypotheses, which of course they are not the first one to come up, is that perhaps there are some sort of internal slab deformation at the depths where you have the highest seismicity. So perhaps you get this kind of dripping effect, and that's where majority of the driving force is coming from. So it's not from the surface deformation, but perhaps from internal slab deformation. So I guess just to quickly summarize here, what we have observed is that in this particular case, the magnitude 7.5 earthquake has a lot of aftershocks. At least in this case, we proved that like some intermediate depth earthquake can have a lot of aftershocks. I mean, it could be that it's there, they haven't been detected or observed. Aftershock sequence follows a Morello decay, and in this case, and it also behaves similarly like shallow seismicity as well. It turned to concentrate to the west of the main shock rupture. It turns out the main event also predominantly propagated to the west as well. So maybe there's some sort of what we call a directivity effect, where when the main shock rupture towards some certain direction, we're going to experience the highest stress perturbations. That's also commonly observed for crustal earthquakes as well. And finally, elevated seismicity in the region is probably likely due to some sort of internal slab deformation. And hence in that case, we can, if this is the case, we can actually use the seismicity here, and hopefully by detecting more events, we can start to look at the problem of other events occur only on a single fault, or maybe there are multiple fault lines here. If so, what can we learn from the seismicities, and also what can we learn about the mechanism for intermediate depth events. So that's kind of the quick, I guess, not quick, but summaries of one of the study we have done very recently. So this we haven't submitted yet, but so what I'll do next is, I guess because I'm a little bit short on time, I'm going to just quickly jump to the second part of my talk, which in this case I'll move to a little bit shallower in the crustal region. Of course, I'm sure most of you know, so I won't go into details. Of how a subducting process looks like. Generally speaking, you have a locked region from surface to, about certain depths, and this region generally locks for 100 years, and then release in a megastress event. That's kind of where we normally know how megastress works, and and below that, you get steady continuous creep, and there's not many seismicity, except you may get some intra-slab seismicity. But of course, things changed, about 10, 15 years ago when people started to put continuous GPS and also continuous seismometers in along the subducting zones. What people found out, which is now typically a iconic picture, is that in cases, this is actually in the Pacific Northwest in Vancouver region. Where you have stations close to the trench, you observe from GPS signals that every 10 or 14 months, you get this kind of GPS reversal. So during this GPS reversal, there is a earthquake of equivalent of magnitude 7 occur, but of course there's no magnitude 7 reported because those are slow earthquake. And during this process, so the events start and unfold itself normally take about 1 to 2 weeks. And during this time period, the seismometer also record those kind of vibrations. And if you track the vibration of the seismometers, you can actually locate them, and in this case, you start from here and then propagate bilaterally in this direction. So, this is now the so-called slow earthquake, but of course it's not a new term. Many years ago, people used stream meters, and they observed slow earthquakes mostly occur on the creeping section of the San Andreas Fault and other regions as well. But of course now with GPS and also seismometer, they found it to be at the lower crust near the Moho, where one of the possible ideas is that in this region perhaps you have maybe highly elevated fluid pressure such that the effective confining pressure stress is so low that you started the fault here behave kind of semi-brittle, semi-ductily, so that it can accumulate some stress, but it cannot accumulate too much. So once every few months or a few years, they will release into this sort of slow seismic event. And while it's sliding, some of them can also produce seismic signals. Because I'm a seismologist, of course, I mostly take care of the seismologic aspect of that. So this gives you a rough idea of where this type of slow, deep, slow earthquake has been observed. And in particular, I'm looking at the tremor activities. They're mostly, of course, along the Pacific, rim, mostly along subducting zones. But of course, right now we also start to observe them in intraplate, inland fault, mostly strike slip fault as well, including, let's say, regions in Java and also, in let's say around the Caribbean, where you have left lateral strike slip fault as well. So this phenomenon are become more observed than compared with before. So, again, in the interest of time, I'll just quickly tell you one very quick story which we recently published to look at this tremor activities at the Parkville section of San Andreas Fault. Again, to orientate you, we're looking at a region roughly here, which is at the transition between the so-called creeping section of the San Andreas Fault, where the fault is continuously sliding without generating very large earthquake. Of course, there are many small, tiny earthquakes, magnitude 2 or 3, hundreds of them per year. To the south of that, you get the the locked zone, which was last ruptured in 1857. So this region, which is the Parkville region, has magnitude 6 earthquake every 20 to 40 years. Of course, tremor was observed there about a few years ago. If you look at again the waveforms, this is how they look like. This is the one recordings of the tremor. So if I don't tell you it's a tremor, you look like it looks like noise, right? It used to be noise, of course, until someday people say, okay, that's a signal, let's study it. The reason we can confirm there's a signal is because if you look at the, I was just saying, it's almost look at a raindrop. If you look at the spectrogram, you can see actually you get these strikes. So those are probably individual small events, but they are also occur so frequently so that they're almost on top of each other. If you look again at multiple stations, this is about 200 seconds of recording. You can see that the recordings are almost similar at different stations. The stations are separated by a few tens of kilometers away. And if you look carefully, you can see that some stations arrive early, some stations arrive later. And if you zoom in further, you can see that again, you see this kind of shapes that give you a rough idea that those are probably sources that come from some common regions. However, if you ask your question to pick them, it's hard to pick them because they come as a group, and sometimes it's hard to separate them because they're on top of each other. So we use the same approach that we described previously, this template match method. Of course, in this case, we don't have a template to start with because you start with nothing. Those are not regular earthquakes, so you cannot use the regular earthquake there to cross-grade and detect. You're not going to detect anything. This is mostly the work that was collaborating with Dave Shetty and USGS. So basically, what he has done is you take a region where you have a lot of tremors. So you can see there are a lot of those coherent signals. Then you zoom in and find the time where it has relatively high peaks. You can see maybe you can pick some event here, but definitely you cannot see where the P wave is. Nevertheless, he cut a window right around those time period and take this window and cross-correlate with the rest time period, assuming that the same signal will repeat at least once or multiple times. And then you stack them. And after you stack, let's say, hundreds of times, this is what it ended up getting. You can see that signal become much clearer, and turn out those are S wave. Sometimes you can start to see P wave as well. So the P waves are probably there, but because they are so close and right on top, so normally speaking, you cannot identify what the P wave is for individual trace. But if you do the stacking multiple times, you can start to identify them. Once you have P wave and S wave, this is how it looks like. If you can start to pick the phase, then you can treat them as regular earthquake, because those signals are turned out, if you locate them, they are turned out to be located in the lower crust. Okay. So this is again the map view, of the region, study region. This is a cross section. The gray are the regular seismicity, the low more brittle regular earthquake. This event goes from about 3 to 15 kilometers, again in the upper brittle crust. Those events, if you use this kind of scanning and matching technique, if you locate them, they are located right around between 20 to 30 kilometers. The mohole depth here is about 25 to 30 kilometers. It's right above the mohole depths. Okay, and those events, they are what you see previously are considered to be. So we have a name called low frequency earthquake. The reason that we call them low frequency is because if you look at the frequency characteristics, it doesn't have as many high frequency as compared with regular earthquake. So one of the studies we have done again recently is to look at this study regions and see how it behaves before and after some regional earthquakes. So in this case, we look at a case where there's a magnitude 6 earthquake in the Napa Valley in 2014. Now, if I remember correctly, I think last time I visited DTM a few years ago, I gave a talk where I used this region and looking at how very large distant earthquakes, like Japan earthquakes or events that are magnitudes 8 or 9 at a very far distance, how that affects seismicity here. Now we're looking at events that are much closer and also in a smaller magnitude range, and see whether the occurrence of this event affects the tremor activities or not. If you look at the catalog, again this is from the USGS, this is a regular earthquake. If you look at the cross section from north to south, you can see this is the geyser, the geothermal region, this is the Lapa region, you can see there's a lot of aftershocks. But if you look at the creeping section and then the Parkville region, if it's a cumulative number, you don't see any clear increase of seismicity. So at least from the catalog, you don't see any clear response from the Napa event which occurred here. However, if you look at the tremor catalog, it's quite different. So what's plotted here are along strike positions. So this northwest southeast, about 150 kilometers. This is time. So from 2010 to 2015. So each, probably you can see each dot represent a detection of a tremor based on this, family of there's about 88 template families. So basically what we have done is to take the waveforms of about those events occur lower crust, and then we cross-correlate with tens of years continuous data. And whenever you detect something that is above the threshold, you register as an event. So you can see there are a lot of events, and sometimes you see this kind of stripes here. Those stripes, we consider them to be a slow slip episode that occur in the region that is south of Parkville. But of course, if you look at the region that highest the signal is here, and this turned out to be right at the time when the Napa event happens. Again, if you look at the cumulative number, the total number is about 300,000 events in the past 4 years. So the number of events is about 100 times more than the regular seismicity, because those events, in a region every few days, you have a repeat of events. So they occur at lower crust. They occur much more frequently than the regular seismicity. Again, if you look, you can see that the largest excursion is here right around the Napa event. You zoom in further. Again, this is the same time plot, but plotted in 2014. Again, the largest excursion occurred right at the time when this magnitude 6 earthquake occurred. The distance is about 300 kilometers. And again, look further. You see, this is the Lapa event. This is Parkfield. You find that, again, you zoom in further. You see in this region immediately north of Parkfield, this tremor activity started immediately afterwards. You have this kind of immediate triggering effect. However, in the south part, where the majority of the activity, you find out that there are some minor sequences occur immediately afterwards, but it takes about 12 hours before this major sequence starts. When they start, you can see clear expansions, indicating that probably there's a weak zone that get initiated, and then you start to see this kind of creep front expanded in space and time. So the common ideas of tremor and where they occur. If you look at again, the kind of the schematic cartoon is that we know that again this is the region where you have the upper crust and lower crust. So turns out most of the tremor mostly occur at a depth around Moho region. So there seems to be a gap, about a few kilometers below the regular seismicity. Regular seismicity go up to about 15, 16 kilometers. Tremors start from about 20, 25 to 30 kilometers. So one of the ideas is perhaps that you get this kind of change of strength, which is here the reduction is probably likely due to increase of pore pressure. But as you go to the lower crust near the Moho, you probably have another slight increase of strength. That's probably where we start to observe those kind of brittle, semi-brittle, and semi-ductile tremor activities. So, to kind of summarize what we have seen here, I hope I convince you that this tremors episode, you can also decompose them into many, many small, tiny, so-called low-frequency events. And those events, if you locate them pretty well, then you can use these techniques and tell you about where exactly this tremor is occurring. And by doing so, you can start to understand and analyze how it's evolving space and time. In this case, I just give you a quick example how a relatively moderate size event, a magnitude 6 earthquake at about a few hundred kilometers, can trigger a major slow steep episode. And the episode lasts for about 1 month or so. So if that's the case, perhaps to tell us that maybe the earthquakes are interacting more often than we normally used to think. Previously, we used to think that only the magnitude 8 or 9 can trigger or initiate this type of sequences. So one of the things that we're still looking at these days is to see, if you have the lower crust that is kind of sliding in this tremor, this slow episode, could this lead to some ruptures in the upper crust where you have brittle failure and magnitude 6 or 7 event? And if so, then maybe by carefully monitoring this sort of tremor sequences, because they are very stress sensitive, and I should point out that those are events. If you have stress perturbation on the order of a few kilopascal or so, then it can modulate and change its behavior. So the tremor are well modulated by solid earth tides, and it's also modulated by sometimes even perturbations from again regional or very large distant event. So because they are stress sensitive, and perhaps we can use that as a stress meter to monitor what's going on in the lower crust, where previously we think it's aseismic, but it turns out they are not. And in certain regions, you have this kind of tiny, small events that are occurring almost daily, that we can use that as a way to monitor what's going on. So I think I'm almost finished my time, so I can maybe stop here. Either I can continue. I have about 5 minutes to talk about the third topic, which is about injection-induced seismicity, or should I continue? Let me take 5 minutes. I know I'm a little bit out of time. So you can see I'm moving closer to shallower. Okay. So now I'm looking at the depth range of about only a few kilometers of depth, and I'm sure most of you know that in the past few years that we are experiencing something we have never seen before, which is in mid-continent, especially of course in Oklahoma, southern Kansas, also some places in Texas, there's a huge increase of seismicity. So if you look at, again, of course, magnitude bigger than 3 earthquakes in the past, let's say a few tens of years, and since about 2008, 2009, there's a huge increase of activity, and this increase is much more than we normally expect from, let's say, background fluctuations. Okay. If you look at, again, where they are, of course, we know that they are mostly occur in places where there's a lot of production from shale gas development. And it turns out that, those, magnitude 3 or 4, sometimes magnitude 5 event. The largest one so far occur is about magnitude 5.8, which occurred last month in Oklahoma. So those are mid-range magnitude events. And turns out that those events are, we believe that are triggered or induced not by, let's say, hydraulic fracturing, but by the wastewater injection, because the general idea is, of course, is that when you start to produce oil and gas in these places, there's a lot of wastewater being produced, and you have to dump them somewhere. And then it turns out the easiest place to go is drill another deeper hole and inject into ground where it's more or less porous, so you can put wastewater there. And of course, by doing so, we know that from previous studies many years ago, like in Colorado and other places, if you inject fluid in the seismogenic zone or above the seismogenic zone, and you can easily change, let's say the Moore diagram to push it to lower and to interact with the failure slope. So in this case, you can, if you are unlucky to be close to a fault that is somewhat critically stressed, you can start to induce seismicity. And so we think that's pretty much what's happening right now. However, if you look where those events are occurring and look at where the active injection is going on, this is a recent paper published last year. So the blue circles are the injection wells. They are almost all over the place. There are hundreds and thousands of them going on. But if you look at this, the yellows are where they consider to be associated with trigger seismicity or induced seismicity. You can see, some regions, this is the concentrated region. Other regions, here in Texas, there's not much going on. Well, I should point out that they're only looking at magnitude bigger than 3 earthquake, right? So maybe they're inducing many small tiny events that are otherwise not made into the catalog. We don't know yet. But at least you see a clear spatial separation. Some regions, for some reason, that you are inducing magnitude 3, 4, 5 event. Other region, maybe you're not inducing any event or inducing very small event. We don't know for sure what's going on. And this is, of course, I know many people are still working on that. We're also currently starting looking into this problem as well. So I'll just give you, again, very quick one examples. What we're doing right now is, of course, we're collaborating with local people here to looking at individual sequences and try to understand, let's say, if I have accurate information about injection history and I would know where the seismicity is, what can we learn about the correlation between the injection and also what the seismicity would look like? So I'm just quickly show one example. This is where the magnitude 5.8 earthquake occurred. It's here within this zone. If you look, you can see that it's probably there's a clear boundary here. So I don't know if this is by coincidence or maybe there's a structural differences between as you go across the major fault there. Again, we do the same thing. You take the events from those magnitudes 3 and 4, which you already have a lot of them. But then you take them and you use them as a template. You can scan through and you can start to detect events roughly in the magnitude of 0 to 1 range. So this is about a factor of 2 increase, about 20 to 100 times more event than previously detected. Now you can start to look at again, spatial and temporal evolutions, because previously you only have a handful of events to look. Now you're within more events, you have better statistics, and then you can look at better how the correlation is with respect to injection history. Again, I won't go into details. This is one example where we're looking at one sequences where you can see that start with seismicity start with here. At the beginning, there's not much. The circles are magnitude bigger than 3.5. You don't have many large events and start with shallow, but gradually with increase of volume of injection, you start to see a kind of a diffusion of seismicity, and also you start to induce more event, a larger event at later times. If you look at also the stress drop, amount of like the stress relief during those small events, you also see clearly at the shallow depths. You can see that you have lower stress drop, but at larger depths, this is probably as you go into the basement rock, you start to observe those events with relatively higher stress drop as compared with before. And finally, of course, you can also look at how the seismicity front evolve in space and time, and try to correlate that with the injection volumes and the history to better understand what's going on. So again, here what we think is going on is that at the beginning, of course, you see some small event get induced right in the top layers, and they generally have relatively small stress drop. But gradually, as you go later in time, you start to trigger event at with larger magnitude and also at larger depth with higher stress drop event as well. So to again quickly summarize what I hopefully show you, is that by using this sort of very simple techniques, we can analyze seismicity at different depths. I start with an intermediate depth event, and at a depth of about 200, 250 kilometers. We can use these techniques and then detect a lot of events and try to use that to understand what the relationship between the seismicities and also the main shock and aftershock sequences. The same techniques, of course, you have to modify a little bit. You can use it to study those so-called deep tectonic tremors that occur in the lower crust along major plate boundary fault. And because they are, again, highly stress sensitive, then we can use it perhaps to monitor during large earthquake cycles. And finally, most of the shallow earthquakes, we see, of course, that again the depth range of about 3 to 5 or 6 kilometers occur right now in Oklahoma and also central U.S. are believed to be mostly driven by poor fluid diffusions associated with wastewater injection. Of course, like I said, we raised some interesting questions. It's unclear why they occur in certain places. Maybe it's related to injecting history. Maybe it's the amount of how fast you inject could control whether you trigger event or not. Could also be associated with subsurface rock type and also stress conditions. Well, that's something we don't know yet, but that's something we can work on in the coming years. So I guess I'll stop here and a little bit lag, so I'll see if I can take any questions.
Great, thank you. Questions? Diana.
Right. Okay.
So, hi, Zhigang.
Yeah.
So, your technique requires essentially a template, which you use a natural earthquake for, and the concern there is, of course, that you're kind of you're only looking for the earthquakes that look like that earthquake,
yes,
and you're missing other ones necessarily, and B, you may not actually be able to have that template. If, for example, you're interested in a region that appears aseismic. So the question is, how well does this work if you generalize to some kind of like generic earthquake or like a wavelet? Can you do that? Have you tried that?
Yeah, that's a good question. So yeah, like I said, one of the limitations of this technique is that you are looking at an event with a lens, right? So you can only look things that are similar to you. So if there are something that occur but is not in your database, then you cannot detect it. So there are two approaches to do this. One is that you can first of all, you can generalize the technique such that you don't have to start with existing template. You can build your template from scratch. So the technique I was talking about in the second subject, where in this case you can almost do it in an automatic fashion, which is you can start by building a template based on some, you can either use some sort of detection in the fixed domain. You can also detect them based on the coherence or similarity across the station. So in this case, you're not looking at detections from the same station at different times. You're looking at the detections across at the same time, but across different stations. Once you start to build up those templates, which hopefully is more complete than what you start with, then you can use this and rescan the technique. So yes, the short answer is there are ways we can definitely go beyond. This is just one technique and seem to work in places where you have a lot of events. So for example, in the case of Oklahoma, we're not shy of event because there are like thousands of magnitude 3 and above event already detected every year. So you have a pretty good coverage of what's going on. However, in certain regions where you don't have it, you can use other techniques to help to start with a template, and then you can use that to do scanning, which can help you to further detect and reduce your detection threshold.
One of your slides showed multiple templates.
Right.
Where did you get those multiple templates?
Yes, I guess I won't go there, but I can. At the early time, you have 3 templates. So all those 3 templates, yes, are from the catalog. So let's say in the regions where you have a lot of events. In the case of Parkville, you have about 100,000 of events already been detected in the past 20 years. So basically, if I go to a region, what I normally do is I select, I just, select all the events I can use, and treat each of them, and then it scans through a year of data, and then I take another event and scans through the year of data. You can see that's a kind of dumb, approach. But of course nowadays, with faster computers, you can do that, in a matter of, let's say, days to weeks. But I haven't got time, to talk about this. But of course, if you go to an even larger region, let's say if you want to detect, let's say the entire California or entire Japan in the past 20 years, you probably need a super computer because you are actually trying to do this kind of matching, and it turns out that this process can be easily parallelized. So right now we're also using GPU clusters to try to take, so that normally you would probably take years to do it, but now you can take days or weeks to finish the job. So, but that's a good question. So we can but we are trying to test every event and make sure that you're not missing any event.
Steve?
I thought that bottoming out of earthquakes in the Parkfield area was extremely interesting, and
Yeah.
the conclusion was that it's due to water and lithostatic pressure at that depth. But it can't only be water, because we have softening due to heat. We also have a lithologic contrast at the moho. Otherwise, if it was just water, it wouldn't care about the moho.
Exactly.
So what's the percentage due to water, and what's the percentage due to
That's a good question. I don't think people have clearly classified what is the contribution from a mechanism versus another. What we do know is, of course, from, let's say, people doing seismic tomography and also using MT, they did find evidence of elevated fluid pressure at middle crust to lower crust in that region. What we don't know is, of course, what is the contribution. And if you look at the tremor depths at, let's say, from here, you can see that pretty much the maximum depth is about 30 kilometers. But if you look at other people's tremor catalog, sometimes they go up to 40 or 50 kilometers. The question is, are these...
Is it error propagation in the catalog?
Well, yeah, part of this is, sometimes, we can constrain the location relatively well, but the depth is not well constrained, depending on what kind of technique you're using. For this technique we're using, we can detect P and S waves, so it's probably more accurate than only you take the so-called envelope function and doing the external cross correlation, because in that case, you can easily get tremor that fluctuate at tens of kilometers. So, yeah, you have to use some certain techniques to have a better constraint about depth. But from what I see in this region and also other region, it seems like the tremor are generally stopped at the depths of where the mantle wave, where the like the moho region is. Whether or not this is a coincidence or maybe it has more physical explanations remain to be tested.
So going deeper, so if you're interested in deep earthquakes, do you still need fluids to drive those swarms? And if so, can you use those swarms to estimate how much water is going?
That's a great question. And like I said, I think some of the models require fluid, some of the models you don't. I would say at this point, of course, we just started looking at this, so we can't tell you again the same question, how much contribution is from fluid and how much does. But one thing we do know is that once we have those events, of course, previously we don't have as many, but now that we have some of them, we can then start doing, let's say, tomographies in these regions, and hopefully that will give you, general tomography will probably give you P wave velocity and S wave velocity, and maybe you'll come with a VP to VS ratio, and so those can perhaps tell you some information about what, whether or not there are, fluid, and if so, what percentage. But we're not there yet. But I do know that I think, once you have as many events, you can use what has been utilized, let's say, for crustal seismicity or region in volcanic region. You can simply take the approach and apply it at larger depths, and that can hopefully give you not only better refined structures. Whether are they right now? It looks like a cloud. I mean, is it a cloud, or maybe you see band of shear zones, and if so, does it tell us what's going on there? So the short answer is, I think that there are a lot of things we can learn, but one thing we could do easily is, once we know the locations better, we can then use that as a way to invert for velocity structure, and hence perhaps provide more estimation of the amount of fluid and also other processes as well.
So you give one example is around 300 kilometers. So obviously
about 200, I guess. Yeah.
So for like the 600 kilometer depths,
right.
Is those being looked at and has similar?
Good question. We just started also last year. I had an undergraduate student from China. So we look at one sequence of event in Russia, where I think 3 years ago there was a magnitude 8.3 earthquake. It's the largest deep earthquake ever recorded, and so we did some quick scanning, and from the data we have looked, I guess the largest aftershock is about 6 or so, but we found about 2 times more events than in the catalog. But if you count the number of events, it's much less than compared with these sequences. So, but of course, I cannot say general. We haven't looked at systematically yet. But at least for that sequences, we do know that in that case, the magnitude 8.3 does not trigger as many aftershocks as we normally expected. For if you have magnitude 8.3 on the near surface, in the crust, you're going to have tons of aftershocks. In that case, we have about 20 to 40 events in the next 10 days or so. So perhaps, at least in some of the case, maybe the lack of aftershocks for certain sequences is probably real. But of course, you probably need to do a more systematic global study with similar techniques, or to try to make sure you're not biased by either station coverage or by the technique. If you're using the technique, you see more. Using the other technique, you see less. So that I think remains to be examined.
The follow-up is like in general, the polar fluid free water is not going to be existing below certain depths.
Yes.
So definitely not 600.
Right.
6 kilometers at 6 GPa, which will be.
Yes. So it's probably you need other mechanisms, right? Other weakening mechanisms. Of course, there are some weakening mechanisms available at certain depths that can explain. So you don't have to have again free water fluid there, but perhaps you need some sort of again weakening mechanism to have some kind of shear slip at 600 or 700 kilometers. So that's something again. Hopefully by just building up more events that can tell us how things evolve in space and time, and do the events repeat in the same region or not, or maybe they change. That will hopefully tell us more about what's going on at those great depths.
John's been
Okay.
raising his hand in the back.
Yeah.
Yeah, it seems like finding some of these large numbers of small earthquakes a useful way to proceed might be to use a machine learning approach, like a neural network or something similar.
Mm-hmm.
That way you may get a more general success than just searching for individual templates, and you can broaden the search
Okay.
for certain characteristics rather than just matching individual templates.
Right. Are you suggesting to generalize a little bit?
Yeah.
Okay. Yes. I guess you're right. So what what we're doing here, of course, is a approach. And of course it works in certain regions. It may not work for other regions. There are, of course, right now we also try to use in certain regions where you have enough recording, density recording, you can come up with alternative method so that you don't have to based upon certain features. I mean the best way, of course, which I don't think we can achieve right now, is if you have very good velocity model, and also then you can potentially generate synthetic seismograms, and then you can use that as a match, or as a way to scan the data and see if the actual recording match with the synthetics now. But of course, right now we can only do this for a very long period. This is actually people have been doing that for, let's say, on a period of about 10 to 50 seconds or so. If you go to higher frequency, you don't have good velocity model, you can't match them. So we have to use this so-called empirical Green's function approach, because each event produces a wiggle that. So another approach that we are trying to do in these days is to take the existing templates at certain regions and try to reconstruct at regions where you don't have it. So you can do some kind of extrapolations. An event here and here, maybe right in the middle where you don't have event, but if you based on the waveforms at nearby regions, you can somehow construct a near complete, let's say, or uniform distribution of template, such that in that case, hopefully you don't have a bias, because otherwise you're only going to see event nearby this region, and in that region you don't have anything in between. But hopefully there's a way you can do some kind of reconstruction of the wave field if you have enough event to do so.
I'm trying to figure out how your method differs to Alvaro's.
Yes.
He didn't have a template, and yet he found all these events.
Yes, that's a good question. Again, I don't know if I can go back. So his techniques basically, which is kind of the classical standard technique, which is they're using the so-called envelope functions, which is that if you have the tremor somewhere. All right. So sorry. So they take a chunk of data. For example, here it's about an hour. Of course, they chop them into like minutes or tenths of minute, and then they take the envelope function and smooth it, and then they use the cross correlation of the envelope function to get differential time.
Yeah.
So in that case, they made several assumptions. They assume here the signal here is dominated by S wave, which generally is the right assumption. They also assume during this time period, tremor doesn't change or move in space and time. But that's a huge assumption because, as I show you, that in some regions during the period of about tens of minutes, tremor can migrate up to tens of kilometers. So in that case, if you're assuming that the whole tremor here come from same region, you're going to get an average location, but you can't tell how it evolves in space and time. So what the technique we're doing here is we're just using this kind of waveform matching to dissect those long enough recordings into small tiny events that are generally, like you treat them as regular earthquake.
I understand that, but Obara's method doesn't require a template.
It does not require a template, yes. So that's exactly. So the advantage of that technique is that it's doing cross-station coherence or detection, so you can apply it very quickly to a region like years of data without no problem. Our techniques are heavily computationally intensive because you're doing this kind of matching and scanning, so it requires much more computational power.
But couldn't you combine the two?
Yes.
Use Obara to find
Exactly.
templates and then you go and look in your
Yes.
method?
So this is exactly what we're doing right now in Taiwan and a few other regions. So we have techniques where we just take the Obara approach, and we found, for example, like out of a year of data, we have maybe 1,000 hours where you have tremor. Then you only focus on those those time periods. You don't have to take the year because that's too much. And then you take the chunk of data within those let's say 1,000 minutes or hours and doing the detection. So in that case, you reduce the continuous data to only a fraction of data where you think there are tremor activities going on. Yeah, so combining those approach can speed up the process much faster.
All right, well, let's thank Zhigang Peng again. And
Well, thank you very much. Yeah,